in virtual creatures than I am. And you're going to give a nice introduction, aren't you, Sam?
Thanks, Kat, for the pre-introduction. So, yep, thank you everyone for attending, and definitely want to thank my co-organizers, Caitlin, Grasso, Kat Walker, and Lana. Lana, I'm sorry, I don't know how to pronounce your last name. Sinapayen?
Sinapayen.
Sinapayen. Okay.
Yeah, perfect.
I felt bad not saying everyone's last name. So, okay. We'll edit this out of the video, Kat, right? Okay, good. So thank you, everyone. And so I was trying to think about what I wanted to say, and I realized that virtual creatures mean a lot of different things to different people. For many at this conference, they're a way to understand life as it could be. And for others, they're a means to an end, useful machines such as robots. And for yet others, they are a form of artistic expression. And like many others, when I first saw Carl Sim's video of evolved virtual creatures, I wasn't exactly sure what it meant, but I knew that I wanted to work on whatever that was. And so this contest and workshop is intended to spark the same kind of inspiration and also advance the field, because frankly, we've struggled as a field to surpass Carl Sim's original work. You go back and look at that video and you watch it and you go and watch some more recent virtual creatures videos, there are advances, but they're very, very similar. If you do the same thing with the performance of neural networks in 1994 versus today, there's some big differences. So this is what makes this problem so interesting. And I hope that this contest can serve as a way to progress the field a little bit more and also to have fun along the way. So that is my big introduction. So now, without further ado, I guess let's watch some cool videos and see the fun stuff.
Fantastic, Sam. Mia, Kathryn, you're up first. Are you ready?
Yeah, I'm ready. I'll just share. I was gonna use my video in the presentation, so I'll just share it myself, right?
Yes, are you able to do so?
I think so. Share sound, optimize for video clip. Sounds good.
Perfect.
Screen 2, share. Okay. Can you see the screen?
Yep, I can see it. That looks fine to me.
Oh, I somehow lost all the cameras, so well, I don't need to see you guys, I guess.
We'll shout if there's a problem.
Oh, okay, that's good. Yeah, I'll just start, I guess. Yeah, so my name is Mia Kathryn. I'm from the University of Oslo, and I'm going to present the work I did with my supervisors, Kyrre Glette and Frank Wienstra, on control in modular robots and their effect on the morphology. Yeah, so I'll just get right into the video because I think this one explains a lot better in 4 minutes what I could do. So yeah, just shout if something's wrong. Oh, sorry. Okay. Oh, sorry. You're all still there, right? Still can't see anyone.
Yeah, no, wait.
Yeah, we here.
Okay, great. Okay, I'll just fill in the gaps that the video left because obviously I can't put everything in the video. So just explain some of the results and go through my conclusions. So starting with the fitness graph, we have fitness on this axis and generations on this axis. And we found that the copy controller outperformed the other controllers, while these ones had no significant difference between them. We also looked at the effect on morphology. And if you look at this graph, we have that I plotted the fitness against the number of modules for all the controllers. And you can see that the centralized and the sign controllers both have very small morphologies, less than 10 modules, but they performed reliably well, not exceptional though. And the copy and the decentralized both had larger morphologies, while only the copy did extremely well with the large morphologies. We also looked at the morphology changes, the beneficial morphology changes across the generations. And we found that the copy controller had more beneficial morphology changes throughout the runs, all the way up until the end, while the centralized had the least. And plus there's some other results from my master thesis work, where in summary, I found that the copy had more unique morphologies throughout the runs compared to the others, about double, while the centralized again had the fewest. And these were pretty similar. So why is there more morphology change in the copy controller? I'll just explain it by looking at the controller mutation and the morphology mutation, comparing the decentralized to the copy. And if you mutate one control unit in the decentralized, one module's behavior changes. While in the copy, mutating one control unit will make a lot of the modules change their behavior. So this means that the copy controller is not able to fine tune. It makes larger jumps in the search space, which is probably good to avoid local optima. And also it makes it rely more on morphological mutations in order to get better. So in the morphology mutation case, you see that I've added one module here from this example. The decentralized CTRNN inherits the control unit of its parent module, which is good because then it gets like a functioning controller, but it might not work in this position. Meanwhile, the copy also does the same, but this control unit has been optimized to work in many different parts of the body, so it's more likely to work in this position, which makes morphology mutation less deleterious, which again encourages morphological exploration. And if we look at the decentralized again, it has a more complex optimization because it needs to synchronize all the different control units, which leads it to sort of fixate on local things. Like, I absolutely love this guy, but he only moves his feet and the rest of him are completely static. And if you compare it to the copy, which moves most of its body at once, you get that this one has a force advantage because it is stronger, it can move further. The centralized CTRNN and sign controller both struggled with local optima solutions. And here are some of them. My data is absolutely filled with this guy. And this is a case of early convergence of morphology. And in this experiment, we can definitely say it's a problem with the controller. The centralized CTRNN had a fixed size topology so that there is no mapping that wouldn't sometimes shift the inputs and outputs when adding a module, which essentially scrambles the controller. And here I just wanted to show some other copy controller performances from a different project. I just think that it has a lot of very interesting behavior, like these sort of dog-like creatures. And a very impressive somersault. This is actually a falling robot. It's not really what I want, but it's still kind of cool. And a cheetah-looking creature. So for future work, I would really like to try with different networks because the CTRNN doesn't exactly have the behavior that I hope it would. And the copy controller could also be researched as a swarm because it has some sort of behavior, like the different control units take on different roles based on their position in the body, which could mean that it is more robust like a swarm would be and more scalable. I would also love to try a centralized version where you grow the topology with the morphology, but with a copy strategy on top of that. So thank you for your attention. I don't know if I went too fast or too slow. I also have a paper on all of this where there are more details.
Thanks. It looks like there's 2 questions in the chat. Lana, do you want to unmute and ask your question? If not, I can ask it for you.
I can ask it, but I think maybe it's faster to read it. But anyway, so thank you for your presentation, and I really like the way the robots are moving. It's very cute. My actual question is, it looks like all of the models converge quite fast.
Yeah.
At about 100 generations, we can guess what kind of locomotion will evolve. Is that correct?
Yeah, I think that's pretty normal in terms of co-optimization. That's a very good observation, but it's like usually you have this problem of the morphology sort of starting to form, and then the controller sort of also starts to decide, and then the rest of it is just sort of optimizing that strategy that it has chosen.
I see. Thank you.
So stop sharing. Oh, I can see you all now.
Can you see the chat? Do you want to read Fabio's? Okay.
Should I answer some of the questions or?
Yes.
Yeah. I was just going to suggest the same thing as Sam did.
Yeah, okay. So the different body species, I'm guessing you mean like the different body types that emerged. That just arises naturally because of the co-optimization. So the body and the brain is not decided when I start, and just something happens.
Oh, that's very cool.
Yeah.
Thank you.
Okay, morphology change over generations. So how did I measure morphology change over generations? Yes, so there was like, I kept track of all the elites from every generation. I had generational replacement, so I didn't really keep the elites, but I saved them on my computer. I could track sort of when a change in the morphology had occurred. So normally it's sort of, at the start, it changes morphology a lot. And then at the end, there's just this one species like line that you sort of follow, and it changes in small ways. So I can sort of track the difference between the morphologies. I made sure to only track the difference between expressed modules, because some of the genome started to bloat with unexpressed modules. So I cut those out. And the population size, yeah, so fitness evaluation, I think it was about 6 million I ended up doing for all of it, but the population size was actually kind of small, 50 individuals in a generation. I wasn't able to have more than that because of the time. This already took a lot of CPU time, so. Yeah, thank you all for your questions, by the way.
No, fantastic. Just before we move on, does anyone have any more questions? We've got a little bit of time at the end of this workshop to have open discussion. So if people do think of questions, or maybe the other contestants will prompt questions that you have for Mia. So we do have time at the end. If not, I think we'll move on. So our next speaker is Naeto. Is that how I say it?
I'm Naoto. Yeah, thank you. Thank you.
Are you ready to give your presentation?
Sure.
Perfect.
So can you see the slide now?
Yes, that looks great.
Looks good.
Yes.
Sorry, maybe I need to share the sound as well. Okay, looks good. Okay, then I'll start the talk. So hello, I'm Naoto from the University of Tokyo. It's a great pleasure sharing our recent research studies on our neural homeostat. It's my, I'll first frame our video as previous presenter and then present an additional explanation, more detail. So, can you hear the sound?
Survival
Yes, we
is the
can
most
hear the
fundamental
sound.
property in animals.
Sure, excellent.
In terms of function, a living animal has the property of not changing its physical state significantly from its ideal state. In physiology, this property is called homeostasis. Homeostat is a concept proposed by Ross Ashby in classical cybernetics. This is a mathematical conceptualization of homeostasis, in which the system controls the internal state to remain within the limited range through its interaction with the outside. However, the homeostat realized at the time was extremely small and difficult to scale. Homeostatic reinforcement learning is a concept proposed in computational neuroscience. In HRL, homeostasis was linked to mechanisms of behavioral learning. This explains the acquisition of animal behavior for homeostasis. Here again, however, the scale-up problem remains unsolved. And this time, we scaled homeostat with deep neural networks, named neural homeostat. This is the result of our neural homeostat agent, which is trained for the homeostasis of two nutrients corresponding to red and blue food. the trajectory of the nutrients is controlled around the origin of the target. The agent receives a laser range sensor for the object, its postural state, and the nutrients inside its body to compute its behavior. The agent learned to walk, navigate to objects, and not to take food. The neural homeostat is a framework for embodied agents to achieve homeostasis through deep reinforcement learning. To do so, the agent receives the following inputs. Interoception, the agent receives the internal state of the body. The agent's goal is to ensure that this does not deviate too much from the set point. Proprioception, the agent also receives joint angles and body posture. Exteroception, the agent receives information about the external world. That is, the rangefinder or vision. The agent converts them into motor outputs by nonlinear processing of the neural network. The performance of the current action is then estimated by the value function module for behavior optimization. Deep convolutional neural networks are used for image input. We found that clamping this agent's sense of nutritional level changed the agent's behavior. This can be used to analyze the agent's behavioral preferences. As a result, we confirmed that the agent dynamically changes its preferences for food, depending on its internal body condition. It can be made into a different problem by changing the agent's sense of internal states. In this environment, the agent has body temperature and needs to regulate it, while regulating the body's internal energy. The neural homeostat maintains homeostasis by feeding while keeping the body temperature constant through behavior. This is an example of the response to a heat shock to a neural homeostat after training. In the simulation, heat is generated in response to the robot's motor output. When the neural homeostat is faced to an increase in body temperature, it lowers its body temperature by temporarily reducing the motor activities. Conversely, when the body temperature is lowered, the neural homeostat shows behavior that increases the body temperature by increasing the motor activities. Using deep convolutional neural networks, we were able to construct an agent whose input was an egocentric vision rather than handcrafted features. This allows the agent to use only the raw sensor data attached to the body, and to extract and use features important for survival. Again, we were able to confirm the homeostasis of the nutritional state in the neural homeostat. We visualized the internal process of an optimized model of the agent, using saliency maps. This allows us to see from which areas of the image the agent is more influenced in its behavior. We can see that the neural homeostat agent decides its behavior by extracting the food of each color, the legs, and the walls in the environment. These do not come from externally given motives, but all come from the agent's goal of survival.
Okay, so in my research, I'm particularly interested in the development of robots, in which the motivation of the robot is integrated and it continually learn and develop behaviors. Actually, such integrated motivation for decision-making in robots were proposed multiple times. Here, I want to extend this as a system for the behavior learning. So is it possible to realize such a system? I believe it is possible. In this talk, I will give an explanation using 3 keywords. The first one is the elementary internal objective for behavior synthesis. And second one is the possibility of adaptive agent during a single life. And finally, the third one is the local information processing. For the first keyword, I chose the survival as the elementary motivation. So is it possible to describe the survival as a learning goal? Concretely, I'm inspired by the idea of behavioral homeostasis, suggested by biologist Kurt Richter. For example, if the rat felt cold, so he finds something to get warm and build a nest in the cage. So that's a problem solving for thermal homeostasis. So this way of thinking was mathematically conceptualized a control problem by Ross Ashby, and the control-theoretic view of survival was investigated in the robots in some previous studies. So, and the recent neuroscience community is starting to discuss the importance of body and homeostasis and survival. So in this way, I picked the survival on the homeostasis as an elementary motivation. Then how should we implement this in robots? So that is related to my second keyword. So regarding the homeostasis, the agent should have a body and the physiological state. The agent has to stabilize this state. To do so, the agent must interact with the environment. This indirect control of the physiological state is our mechanism of behavioral synthesis. More formally, if the agent is living in the environment a very long time, so the agent's physiological state may have a stationary distribution. So the survival overall of the agent may be represented by keeping the physiological state not so significantly far from this distribution. Using some assumption, we can describe the objective for realizing this control problem as we can show this sequential decision-making problem. So this objective can be optimized using the computational reinforcement learning algorithms. So this means this is the answer to the my second keyword. So we can improve the agent during his lifetime. So the reinforcement learning theory plus homeostasis as proposed by previous researchers, this is named the homeostatic reinforcement learning as in the video. So we scale this idea with deep reinforcement learning, and we enabled the agent to control the physiological state using the egocentric information. This is our final keyword, local information processing for survival. So it's maybe I want to talk a bit about the ESCS. So neural homeostasis is still a very tiny system, but I believe we should be careful about this ESCS aspect, because Frankenstein's monster in the novel was created using physiology and electronic engineering, and neural homeostasis is a kind of the physiology and the latest computer science. So maybe a bit longer in the slide. So finally, in this talk, we share our neural homeostasis from 3 keywords. So agents generate motivation for survival, and the possibility of learning during a single life, and finally, the local egocentric information processing. So this is my end of the slide. So thank you for listening.
Thank you so much. I have to say, like, I think all the contestants this year, their talks have been so interesting and really diverse as well. Lana has posted a couple of questions in the chat. Are you happy just to answer them from
Yes.
Yeah, perfect.
Yes. The first question is what are the variable sensor for the interoception? So actually, I'm using just very simple nutritional dynamics in the agent. So
sorry, maybe I can expand
right.
a bit on that question. I wanted to ask, like,
Yes,
is it
yes.
the amount of blue and red food, or like I can't really imagine what were the variables for the interoception.
So actually, it's very simple. So it's the agent nutritional state is just linearly decaying in that along with time, and when as it get some food, he get some the nutrition is recharged in some amount. Actually, it's inspired by other very related work, and I'm setting the same parameter in the agent.
Right. And you also,
So,
I mean, you had many different experiments. So I think you also mentioned temperature, like maybe internal temperature.
Yeah. Actually, sorry for very brief explanation. So yeah. Actually, in the temperature simulation, I actually use the simulation of the reptile body temperature dynamics in the other field. So I implemented that dynamics into the anti-agent and actually it's simulating the body temperature. There is a sunny and also some ground and some reflection is also included in the model. Yes.
That's great. Thank you.
And the final question is what simulator did you use? I just use a Mushoko simulator. It's actually very common physical simulator in the reinforcement learning field. So you can use freely. You can freely use it in your computer.
Okay, if there is
Sure.
time for just one more question. My second question was
Yes.
at some point you said, I mean, you had so many interesting simulations. I hope there's a paper somewhere.
It's my pleasure.
Yeah. So you said to regulate the internal temperature, the agent started moving more when it was
Yes.
cold. Did you see what kind of motion it was? Like, is it random motion or is it like
Okay.
running faster or something like that?
That's a good question. So I actually did not analyze the detail, but when I analyzed just magnitude of I analyzed just the magnitude of the motor output. So when he get some increase of the temperature, he decreases the motor activities. So I guess that's kind of the simple relationship.
Okay, thank you.
Okay, just a moment's pause for any more questions, but if not, I think we're going to move on to Federico. You're next, aren't you?
Yeah.
Are you here?
Yes.
Perfect.
Try to screen share. Okay.
Yeah, that's all looking good for me.
Okay. Do you all see my screen?
Yeah, it looks good.
Okay, so hello everybody, my name is Federico Pigozzi, and what I'm going to talk now is my submission on a potential new paradigm for the modeling of soft agents. And this is actually a shorter version of a presentation I already gave at ALife. So if there is some overlapping, I hope you will find it entertaining as well. And let's start from the motivation. And what we all know is that softness is one of the greatest gifts of Mother Nature. Indeed, nearly every living being is made up mostly of soft tissues. And here I report a notable example from which usually Mike Levin gives at his talks. And this is Lacrimaria, a protozoan, and it is capable of grasping hard-to-reach prey by means of its soft flagellum. Moreover, a new generation of soft robots has sprung up, as we all know, and they promise to achieve very interesting properties, like, for example, reconfigurability, recovery from damages, and safety. Still, if we look at the current state of the art in soft agents research, we discover the simulation and optimization of soft agents pose unique challenges. In particular, no analytical methods exist, as soft tissues imply infinite degrees of freedom and hard to simulate dynamics. Moreover, the embodied condition paradigm, which posits a deep entanglement between the brain and the body of an embodied agent, makes any co-optimization of brain and body arduous, as we all know, since we all deal with virtual creatures. This is something all of us know very, very well. But also, according to the literature, effectively achieving shape change is still an open issue. And so, indeed, overcoming all of these challenges is the question we set out to answer in this work, and also its main potential contribution, that is, developing a novel formalism for the study of soft body agents, namely pressure-based soft agents. And in doing so, we borrow from the field of computer graphics, where different formalisms do indeed exist, like, for example, the voxel-based formalism, but also the pressure model of soft body simulation, which is nearly 20 years old, and is very suitable for the simulation of soft bodies, like, for example, balloons, as we can see from this very short video. Going more into the detail, so how can we describe the morphology of a pressure-based agent? So here is the depiction. So we start with an envelope surrounding our agent, and this envelope is made up of rigid bodies, the red squares here in the simulation, and these bodies endow the agent with a mass, with a sense of embodiment, and so allow it not only to collide with other objects, but also to have a sense of what are its boundaries, okay? But we also have springs, that are the white strings here in the simulation connecting the masses 2 by 2. And springs, as you know, they oscillate, they contract and expand, and in doing so, they actually allow us to model softness because they allow the agent to assume an infinite gamut of shapes. Still, there is one missing element here, that is gas. So in the simulation, we simulate gas inside the envelope, accepting pressure from the inside towards the outside. And in this way, the pressure model of soft agent endows the agent with a structure. Because if there were no gas, if there was no pressure, so as we can see here, the envelope would simply collapse and the agent wouldn't exist. But once we increase pressure, as we can see here comes an agent. Here the agent comes to life. The agent has a structure and can potentially accomplish a task. So then the main point of this work was putting what happens if we put a controller inside our agent and optimize it for a task. And in fact, the main research questions we set out to answer are, first of all, can we optimize pressure-based soft agents for a given task? Do they show a minimal level of cognition when optimized for a given task? And secondly, second but not less important, can we effectively exploit shape change for this kind of robot? Shape change, as I already mentioned, is the hallmark of soft robotics, and this is what we set out to answer in this work. And to this end, what we did was, first of all, endowing our agents with sensing capacities. Why? Because by means of sensing, they can receive feedback from the environment and can potentially send the feedback from the environment back in forms of action. So they can participate in a control loop and so be optimized for a given task. And to do so, we equip the masses, they have the rigid bodies with sensors. In particular, we use touch, velocity, and relative position relative to the center of mass sensors. We also endow our agents with a controller, with a brain, and in particular, we instantiate it with a multi-layer perceptron that receives as input the sensor readings coming from all of the rigid bodies, so we concatenate all of them together, okay? And this multi-layer perceptron will output actuation in a form we shall see later on. And finally, we perform optimization for a given task. That is, we optimize the controller parameters, it has the weights and biases of the neural network with CMAS, that is an established numerical optimizer, but in theory, any numerical optimizer is possible. And finally, so this is what I anticipated before, actuation outputted, it is the output of the controller. What is interesting about these agents is that the actuation is both local on one side, that is, the controller can change the resting length of springs at a given time step. And why this is important? Because as we shall see later on, this allows the agent to initiate a movement to explore its environment. But also on the other side, the actuation can be global. And this takes the form of changing internal pressure. So as we can see in the previous movie, so we have this form of global actuation. It is very important because it allows the agent to morph, to change its shape. And then before moving on to the results, here is the experimental setup. So we tested with 3 different shapes, small, medium, and large, on 2 different tasks. So on one side, we want locomotion on hilly terrain, depicted here, and this is for the sake of the first research question, because being terrain stochastic, being terrain stochastically hilly, we require the agent to display a minimal level of cognition if it wants to succeed in this environment. It is not a mere flat terrain. And finally, for the sake of the second research question, that is shape change, we test with an escape from cage task, depicted here on the right. In escape, the agent is placed at the center of a cage, okay, the blue immovable stuff here. There are two apertures in the walls, and the agent must squeeze through them. But notice the apertures are such that if there was no shape change, this task would not be solvable. And as a detail here, fitness function is maximizing the X velocity in both scenarios, in both experiments. We perform 5 evolutionary rounds of 10,000 fitness evaluations each. And what we discover is that we can indeed optimize pressure base of the agents to locomote on hilly terrain. And here is actually a funny visual creature visualization. This is actually one of the best individuals. And as you can see, the strategy it came up with is rolling over itself. And in doing so, it stretches the springs on the back of its body, and it contracts the springs on the front of its body to produce a kind of rolling behavior. And we also find the behaviors to be really lifelike, to kind of resemble those of biological cells. So it is kind of using its soft body to probe the terrain in front of itself. But we also find the pressure base of the agents can escape from a cage. So here so here it is actually decreasing pressure to shrink its size and squeeze through the aperture. And we find the behaviors to be really lifelike. Here I'm comparing their squeezing abilities to the incredible squeezing abilities of cephalopods. Okay. And we envision many exciting applications in the future, as many soft robots do indeed rely on pressure for the sake of shape change, but also many exciting ALife applications, like the modeling of biological cells. The code is publicly available, and I thank you for your attention.
Thank you so much, Federico. Do we have any questions in the chat?
I don't see the chat, so can you please read?
Any? No. Does anyone have any that they want to ask now? Otherwise, I'll hog the question section. Oh, I think one message is just appeared.
So Mia is asking what were the sensors in the rigid bodies. So we used the touch sensor, that is 1 if you're touching another rigid body, 0 if not. Velocity sensor, both on the X direction as well as the Y direction, okay? And the relative position sensor. So at a given time step, you take the center of mass of the robot, and you take and you compute the distance from the mass you're computing the sensor for. Yeah, and that's the relative position sensor, yeah, both over X and Y. So you have 5 sensor readings for every mass.
I was wondering, how did you decide on how many masses that you had in your system?
Yeah,
and also, I hope you didn't touch on this and I just missed it. The other thing I was wondering, you said it's a mass chain system. What's the stiffness of the links between the masses? Is this something you experimented with different values, or?
Okay, so yeah, the stiffness, I set it to the frequency is 8 Hertz, okay? Damping ratio is 0.3, and they are both related to stiffness. And this is something I experimented a little bit with trial and error, but then I basically settled in these values because they are the same values that I use in my 2-dimensional voxel-based simulator, where voxels are also simulated with masses connected by springs, okay? So this value seems to work well in these simulations. And to answer the first question about the size, yes, the number of masses is basically a free parameter. A parameter is a hyperparameter for the shape. And as I mentioned before, in the full paper, I experimented with 3 different shapes of, in the sense, number of rigid bodies to have like a wide array of morphological conditions. I hope that answers your question.
Yes, yeah, thank you.
Great.
Thank you. Okay, if we have no other questions, I think we'll move on to our final contestant, which is Ping Chan. Are you there?
Yes. Let me share my screen. I'll play the video first. And
Just to
Okay, thank you guys for watching. I bet you guys are interested about what is how does the implementation works. So okay, so here we go. How to design your own fish step by step. Let's first go through the system overview of our work, and the red arrow represents the direction of the forward simulation. And in our method, the user first input a few base shapes to define the soft swimmer's geometry, and the base shapes are interpolated using Wasserstein barycentric interpolation to generate the design. And then the user will define the controller either in an open loop style or in a closed loop style, taking sensor data as input. And the geometry and the control are then simulated for multiple time steps by differentiable simulation and for soft body physics. And the user then provides the loss function to optimize. Because of the differentiability of the whole pipeline, we are unable to back propagate the gradient through the loss function to the geometric design and controller design. And the direction of the backward propagation is denoted by yellow arrows. And therefore, with the gradient descent method updating the design and control, the system will result in a soft underwater swimmer with desired techniques efficiently. Okay, then we dive deep into our method step by step. First, let's focus on the design space. Let's first see what will happen if we directly use the raw voxel design space. Imagine that we have a voxel space with a width of 100, and then the number of parameters well to optimize is 1 million. This is clearly an infeasible problem to solve. So we propose to represent the design space in an interpolation way. For example, the design space is spanned by 3 bases, and there will be only 3 parameters controlling the design space. And we choose Wasserstein barycentric interpolation to construct the design space, because first, it is low dimensional, and second, it is smooth. And we also found that it can be differentiated. So, and also the actuators are interpolated in the similar way. The next part is control. In this work, we use the 2 kinds of controlling style. The first one is open loop, and second one is the closed loop. Open loop controller is parameterized by a sine function. And for the closed loop controller, we use a neural network as the backbone and infer the corresponding actions from the sensor states and an additional bio-inspired temporal encoding. And the temporal encoding explicitly takes time into account by generating a series of Fourier features in different frequencies. It eases the training of the neural network controller by mimicking the periodic behavior of the underwater creatures. And last is the simulation. We choose to build the differentiable simulation upon off-the-shelf differentiable projective dynamic solver for fast inference and simple development for soft body physics. And then it completes our loop. We can use our method for various tasks and different geometries. And for example, in this one, as I showed in the video, the swimmers are initially swimming very slow, and then after a few iterations of training, for example, for the first 3, we are just training their controller, and for the last one, we co-optimize its control and design, and accordingly, our method will generate interesting designs and controls. Thank you for watching, and our code is released on the website, and for more detail, please check our website and paper. Thank you.
Fantastic, thank you. I think you've got a couple of questions from Lana in the chat. Can you see them? Otherwise,
Yes.
I can now.
The tail seems to be the main mean of proportion to an analogy that primarily use the fin in the head. Yeah, for the most creatures, we did found that the tail is the main proportion. And for example, for example, for the orca and the shark and the golden fish, and but for example, in these ones, in the we're showing here, the manta ray and also this normal fish, we actually added the actuator on the side fins. And you can see that after a few iterations, they are actually using their side wings. And also in this one, and on the last one, they are using their side wings to, actually they are not using them as the propulsion, the forward propulsion. They use them to balance themselves from deviating to other directions. So I think they are useful. And if we add more, we did not explore it on that direction. But if we add more actuators on other places, the fish, I think itself can find that it can have other means of going forward. And the other question is, how many times does the optimization takes? Different task has different number of different time to optimize, and for our for example, if you are optimizing for a very small number of voxels, that's because that requires less computations, and it will take you around 1 hour for optimization. And for example, in this one, this is actually one of the most complex example in our paper, and it took me around 2 hours to 3 hours to optimize. And the mean time is cost on the simulation side, and but our optimization only runs for, I think, 20 iterations to 30 iterations for convergence.
Thank you. It's super interesting.
Thank you. Thank you for the questions.
Fantastic. Thank you so much. So that was all our finalists for this year's Virtual Creatures competition. And I have to say, as like I said before, really impressed about the range of different submissions. I think they're all quite different, approaching different aspects of virtual creatures. So in hope to prompt a bit of a discussion from not only our contestants, but everybody else that's in this room, I have a question for, like a global question for each of the contestants, and then maybe other people can jump in. So I was wondering myself this morning, why do we study virtual creatures? What do you think the most important outcome of studying virtual creatures is? Mia, do you want to go first?
Me?
Yeah.
I had to wonder why I do it. I just recently started. This was part of my master thesis work, and I guess I think it's very fun. That's my main reason. But I really hope that we can get some sort of, I'm thinking specifically about like modular robots and how they can be co-optimized, and that we can get sort of robots as tools in our everyday life. So we could have sort of like a modular robot, for example, that can sort of reconfigure itself into various forms. It could be something like a smartphone that you sort of carry around with you and that could help you, which is what I want. I don't think that's the most important thing, but it's what I want.
No, that's fair enough. I think initially I was also attracted because they're fun. But what about you, Federico? Why do you study virtual creatures? What is the point of them? Are they useful, or are they just fun?
Oh, I study them because it's fun. But in terms of usefulness, I think probably one very important application of them that is maybe sometimes overlooked is that they can be very useful, I think, to investigate questions related to evolutionary biology. questions related to life and evolution in general, as the main problem there is that investigating these questions in vivo requires quite a lot of time, you know, because evolutionary processes operate over a very long time scale. And I actually have some papers in mind that really did a very good job at using virtual creatures so for investigating, I repeat it, evolutionary biology questions. Like, for example, the development paper from Kriegman here and many others. Mm-hmm.
And Ping-Chuan, what do you think? Fun or useful, or both?
I think both, mostly fun. And every time I'm training my creature, I actually always expect that it should convert to something that looks like real life creatures. But at some time points, I also expect it to. I always want it to be unnatural and looks very surprising because they are computationally optimized. And however, in our life, the evolution can meet a lot of local minimums. And I always wanted to say that maybe our evolution is wrong. Maybe our probably there's something happens in the process, and actually what we should look like is another form instead of what we are looking at now. So it is, I think it is interesting to see, interesting to be researched, and probably useful for evaluating our evolution and also telling us what we should look like and what we could look like.
Sorry, muted myself. Neeta, final comments on this question?
Yeah, actually, so me too. So me also very fun. It's virtual creature is a fun stuff. So and just kind of the machine learning theory. Sometimes we just optimize something, some recognition or something like that. But I'm very stick at this kind of behavioral optimization because it is fun, and also especially I'm very interested about the integrated motivation of the agent. So it is also very interesting topic in the neuroscience, and also so when I was in the robotics, so I was when I was a kind of the robotics and software engineer of the robotics company. So integration of that kind of the motivation is really difficult because many kind of the behavior can be made, but how to integrate it's not that trivial problem. So, and personally, from that kind of experience motivates me to kind of the integrated motivation. So it's a kind of the practical aspect.
I'm not part of the participants, but I want to answer your question as well, because I think it's a really important question.
I think people would join in.
I don't often do research with virtual creatures, but I think it's actually the ultimate benchmark of most of the synthetic science that are, AI and ALife, because ultimately what we want to do is to create a virtual creature that is appealing and not necessarily cute, but usually it's also cute and looks like it's alive. And I think all of the AI and ALife research converges to this. If you have a very awesome AI algorithm, my first question would be, okay, it's very nice, but can it control this, awesome, cute virtual creature? So it's fun, I agree, but it's also like the ultimate goal, I think, of our research field.
Sam, do you have any comments on this?
I agree with everyone. Yeah, yeah. Lana's point is really good, especially like we haven't created any artificial systems. We haven't created any like physical artifacts that you would confuse with an organism for more than a second. Why? Seems like it shouldn't be that difficult. it's like a physical Turing test or something. Maybe that's the real Turing test we should be chasing, is the Sims test. I don't know, but yeah, it's certainly interesting research, and I think it has important implications for science and AI and robotics and everything else. The question is, do we want everyone else to catch on? What's going to happen if this turns into the next deep learning? I guess it's good to be here first, but we'll see what happens. I think this kind of work, especially Ping Chong, your work with incorporating gradients is going to be important to get the wider ML community interested. Sometimes they don't like evolution. Doesn't seem rigorous enough. I'm not quite sure what the pain points are, but I think like bringing these communities together would be really beneficial for both communities. So that's what I look forward to.
So I think, oh, sorry, was someone about to say something?
Yeah, I wanted also to ask a general question to the contestant. What is the most surprising thing that happened while you were doing this research? Like you were doing your research and then something like really surprised you? Maybe starting in reverse order. So Naoto.
Just a moment. So most actually, so initially I could not expect that we can actually optimize this kind of the whole regular robot for the homeostasis, just using the homeostasis as an objective. So actually, most surprise of my research was that we could actually optimize the agent. So because the agent actually optimize the agent but just by using the homeostasis. So it was my surprise. So because so optimization itself is just using the homeostasis. It's a stability of the internal condition, but actually it emerged the locomotion. So that is my point and very interesting about it.
And I forgot who was before you. So maybe Ping Chong?
Yeah, and I think the most interesting thing that happens in this research, that is one of feature in the controller. Let me share my screen again. So that is this one, and it's called temporal encoding. And as I said in the presentation, this one is actually a bio-inspired technique that we use for neural network training. And this is a bio-inspired because it takes the time into account and explicitly telling the creature that it should work in a periodic way. And actually, without this feature, the neural network controller does not work. It just directly fall into some local minimum that looks like white noise and that's not moving forward. But after we're adding this, the neural network can tell itself that it should look like periodic movements, and it learns that it should periodically move. So I think that this is a very interesting finding. And after we found this technique, that we also think that human brain should also has such a feature that, for example, when you are walking, when you are running, that is a periodic movement. And it should also have this feature that is the training of your neural network, your brain. So this is very interesting to see.
So the importance of time.
Yeah.
Federico?
Yeah, just like an auto, probably the most surprising thing that happened was actually being able to control the kind of agents I presented before. I actually had started that project as a fun project, as a part-time project, and I never expected to be able to control like a blob of springs and masses with a standard multiplier perceptor and a plain optimization algorithm like CMAS. So it probably was the most surprising part of that. Yeah.
So we have two answers that I'm very surprised that my research worked.
Yeah, exactly.
It shows that you're willing to take risks, I guess. Mia?
Yeah, I kind of agree with Federico, to be honest. It's like I hooked up all the networks and everything to my robots, and I was like, they just keep flopping over. I have no hope. And then I ran them, and suddenly they were all moving in different ways. And I was like, oh, I mean, I guess it was bound to happen, but it was still very surprising.
Do we have any other questions, maybe from the floor? Kind of general virtual creature questions? Okay, so another one from me then for all our contestants. What do you want to do next with your research? And what do you think the biggest challenge you might face in achieving what comes next would be? We'll go back down the line. So Mia, you're up again.
With this research specifically, I already said what I wanted to do in my future work, but the one thing I really wanted to do was research the copy controller as a swarm. That's like my main sticking point, because it was originally what I wanted to do when I designed the controller, and then I just forgot for 2 years. And then afterwards I was like, oh, it works like a swarm. So like, I mean, that's one of the problems with virtual creatures is they are not very scalable. And this, like, viewing it as instead just a collection of small robots, viewing it as a swarm could help this along. So I would really love to do that. I don't know if I'll be able to though.
Fair enough. Yeah, I think that sounds really cool as well. And then who was next? It was
Yeah.
Yes.
I was next. Yeah, so the next step I would like to take would be like to attempt the fabrication for these kind of robots. And we're already taking some steps in the direction, and of course, yeah, that is going to be very difficult. I mean, Centuria is like the most difficult thing you can do in robotics, so that's the main challenge. Yeah.
And then final two contestants. I can't remember which order you were in, so whichever one of you wants to answer first.
Okay, I talk. So my next step will be I think actually have multiple direction, but I'm specifically interested about implement our method into the real robot. So actually in my simulation, it's kind of the still my algorithm is very data inefficient, but in the simulation, I assume the kind of the energy dynamics was implemented in the simulation. It's very given by the designer, but in the real robot, the battery dynamics is actually given by its real battery dynamics or that's kind of things. So I'm really interested about how to implement my idea into the real robot and the behavior generation.
I think on the simulation side, there's a lot of things to do. For example, always exploring more shapes and always exploring more controllers and faster simulation and the better differentiation. But I think the most important next steps are actually bringing it to real life. And we have been fabricating some of the fishes and identifying the system parameters out of this. And we actually had a few follow-up works after this one that is minimizing the sim to real gaps. And so I think it is exciting to actually bring something you design in the simulation to the real world.
Fantastic, thank you. Okay, which means that this workshop is coming to a bit of a close now. So before I hand over to Lana to reveal the winner, I'd just like to take the moment to thank our judges which was Josie Hughes, Deepak Pathak, Rob McCurdy, and Christina Shea. And they were judging, for those who don't know, on perceived aliveness, technical achievement, aesthetic appeal, and innovation. So Lana, do you want to reveal the winner?
Right, so I will announce the whole classment, starting with the winner. So the winner is Difakwa by Ping Chuan. Congratulations. So
Thank
you
you.
win this year's virtual creature competition.
Thank you very much.
And in second place, we have Shape, Change, and Control of Pressure-Based Soft Agents by Federico. Congratulations.
Thank you.
Third place is Neural Homeostat by Naoto. And fourth place is Centralized and Decentralized Control in Modular Robots and Their Effect on Morphology by Mia. Thank you everyone for sending your contributions, by the way. It was all like, I think it was pretty high, the level this year.
I agree. Looking at like the different scores for each of them, it was actually really tight. So yeah. Okay, so I think we'll wrap it up there then. Thank you ever so much, everyone, for attending. Thank you for my co-organisers, Lana and Sam. And hopefully we will see you all next year.
Thank you, everyone. I hope you enjoyed.
Thanks,
if you
everyone.
could attend the ALife
Thank you.
conference.
Thank you.